So this is a small talk, a reserve paper actually, that we put in late on the iPhone and Android exploitation going on targeting Uighur Muslims and Tibetans inside and outside the People's Republic of China. About me, I am a PhD student at the University of Illinois. I also run the threat research team at ThreatStop, and I have my own company that sells threat feeds, so I have a variety of hats. Today I'm here as a graduate student. This talk is TLP white. Say anything you want about it. Most of it is using research that was in part done by others, so all of this you can consider public records. There's nothing overtly confidential about what I'm going to say. Obviously, the entire body of this research started with work from Google Project Zero, who discovered iPhone vulnerabilities, or 5 specific chains that we'll talk about. Volexity followed that up with the Attribution and Android pieces of it. Citizen Lab came out with their report a week ago, a little more than a week ago, that covers the Tibetan angle of all of this. So lots of people contributed to this, and I want to make sure that they get their credit and not have people think that this is all mine. There's lots of people who've been working on it, and all started when Google Project Zero went public with their findings. And I wanted to start with one dishonorable mention, which was Apple's response. As far as the problems we deal with in computer security, right, the loss of information, the stakes are usually measured in dollars. When you're dealing with vulnerabilities that are used in what would be interpreted in the West as human rights violations, that's kind of a worst case scenario. So there's lots of good ways to respond to vulnerabilities being disclosed. This was not one of those ways. So I wanted to mention that, right? Because the stakes of this particular class of vulnerabilities, or at least the campaign that's going on, and the context in which it is taking place inside of China. So as far as agenda, we'll talk a little bit about the victimology and attribution, the C2 infrastructure, the exploit chains in iPhone, the Android piece of this, and a little bit of the malware. It's a lot of content packed in 30 minutes, so hopefully I will do it all justice, but you could easily talk for hours on all of this. You could probably talk an hour just on a single exploit chain for the iPhone. As has been publicly reported, the Project Zero initial disclosures for that iPhone malware was targeted primarily at Uighur Muslims. Citizen Lab came out 9 days ago and mentioned the campaigns they saw in Tibet. They have been going on and off for about 5 years, as far as anybody has been able to tell. When Google went public with their findings with Project Zero, members of likely the US intelligence community came in and said, yes, this is Uighur Muslims. There's thought to be potentially 2 different groups with some interesting overlaps in other APT actors that are generally thought to be Chinese-backed. Citizen Lab calls them Poison Carp. Volexity calls them Evil Eye. As is usual, companies will name their own actors, and those names seldom overlap. One of the findings of Volexity was that a compromised website for a brief period of time had the Scanbox framework installed on it, which is used by Comment Crew. So there might be a relationship there, but not enough data to really make anything overly firm about that. But certainly the groups involved in this are almost certainly state-sponsored, or at least state-backed in some way by the People's Republic of China. Simply just by the groups themselves, it's highly suggestive who's actually behind these campaigns. They compromised several websites, the Uyghur portion of this campaign anyway did, that are typically used by Muslims in the region to get news. That being said, there didn't appear to be any checking to make sure that the victims were inside the territorial space of the PRC, so it is possible that others who happen to be interested in the issue, but operating outside the PRC, journalists, whoever, may have been compromised as well. But you can see from the list of websites, and that's not all of them, that's just a subset. The Tibetan piece of this didn't compromise any websites. It was all based on messaging, where somebody in WeChat or WhatsApp would send links to articles. In one case, it was somebody posing as a journalist, sending a message to a member of the Tibetan parliament saying, can you verify this story, as a way to get them to a compromised website. But between the two campaigns against the Uyghurs and the Tibetans, the malware was related or the same. There were different versions. They had the same functionality more or less, but the one targeting the Uyghurs had a little bit more development that had taken place by then. And there was a prevalence of one particular website that overlapped both campaigns. The compromised websites would use the invisible iframes that we all know and love to be loaded on otherwise valid sites. Occasionally, those iframes would use iterations of the actual domain of the compromised websites. Replacing I for L was common. That was primarily in the ones deploying Android malware. Some of the compromised websites pointed you to nothing overly sophisticated, but your typical Oauth page saying log in with your Google, Facebook, or whatever account to get access, so that an app would be installed with permissions to read your entire Facebook profile or send and receive Gmail messages. And of course, then they had access, and it was a malwareless compromise that would persist until somebody went back in. That was nothing particularly sophisticated, but was part of this campaign, which is why I mention it. The compromised websites or the JavaScript did analyze victims for some degree of suitability. We don't really know how much, because by the time many researchers got to these sites, they were already taken down or offline. But there appeared to at least be blacklisting of researchers where we come from an IP and they know it's us, and they wouldn't deliver malware or wouldn't deliver malware to the same IPs repeatedly in ways to thwart researchers. But it didn't have any geographic, or it didn't appear to have any geographic bounding to say, I only want to compromise people inside of territorial China. As I referenced earlier, as some of the reporting on this started coming out, the FBI apparently had asked Google not to index some of these sites because people were going to them and getting compromised unknowingly. So these campaigns were known about privately before anybody came public with the research, which I guess is a good thing, except that it's unclear what was done to protect anybody about it. The C2 infrastructure used a variety of domains. Some were dynamic DNS, the EasyUA.com, MSAP services, overlapped several campaigns, which allowed for at least some indication of correlation between the actors. You have a list of IP addresses there also. Most of them mapped to Chupa in the United States and IT7 networks in Canada. But none of them were seen in previous campaigns of any noteworthiness. So there wasn't really anything to map backwards infrastructure-wise to link to previous operations. If you want to look for infrastructure, I assume that the attackers won't do this anymore, but they use two different email addresses to register domains, which you can search for. There are OAuth indicators because that has to be tied to an email address. You see the 5 Gmail accounts there that were used between the Tibetan and the Uighur Muslim campaigns. You see down here, the last one is ish, looking Uyghur-ish in terms of its nomenclature. So, moving on to the iPhone exploit chains, right? Originally reported by Project Zero. There were 5 different chains of them, covering 14 different exploits, 7 for Safari, 5 for the kernel, 2 sandbox escapes, affecting iOS 12 up to iOS 12.1.2. The different chains affected different brands of versions. What you see in the chart here is what Google published, which is why the reporting said this is going on for 3 years, more or less constantly, which is probably not accurate. What this graph shows you is the windows between the OS release and when it was patched. So, of course, users don't update all the time, so you can be victimized after a patch is released. And it's doubtful that they had access to these vulnerabilities on day 0 of a release. This is what Google published, but Apple does have a point saying, well, we only think the compromise happened in smaller windows, which is probably more reflective of reality. There was periods of compromise where they tried to get as much as they can, and then things got patched. And Apple was pretty quick about getting this stuff patched as they were made aware, and in many cases they were aware of vulnerabilities before they were being reported to them by Project Zero or other researchers. I guess I went through these points already. The important thing is that the attackers did keep persisting in their development. Instead of, hey, I got an exploit and then just went away, they kept finding and developing new exploits. And as we go through the chains, they reuse some of the techniques in the chains that are harder to patch or fix. But they kept at it. The Android piece of this involved exploits all the way back from Chrome 39 in 2014 with gaps again in Windows where there apparently wasn't any vulnerability that they can exploit. But the important thing is the persistence and the effort this group did in continuing to exploit this population to do their surveillance, and we'll talk about the malware and what it did. The first exploit chain affected versions 10.01 to 10.11. Primarily, the initial part of the chain was a heap overflow in the device driver for an Apple iPhone in the GPU of AGX allocation list 2 and shared resource list. That takes two arguments, which is a resource list header, or one of which is the resource list header, which the attacker controls. For whatever reason, it actually allocated seven headers, but was only checking for 6, which meant the attacker could pass in additional information, which allowed them to go down the chain of exploitation. They ultimately used that to allocate 2 shared memory regions, and then start 100 threads to groom the heap for exploitation. And they also abuse how mock, the kernel messages, can have out-of-line data. So a lot of the exploit chains involve overriding pointers or dangling pointers that allow them to continue going down to get further into ultimately executing code outside of a sandbox. And one of the techniques they use in all 5 chains to deal with the process level sandboxing is enumerating the entire process structure, which has a label under ucreds that deal with its permissions. They copy the permission, the sandbox permissions for launch D and put them in place. In the first chain, they never change it back. They just leave it with launch D's permissions. In the other 4 chains, they actually rewrite it back to something valid. But it doesn't persist across reboots. So if you got this malware on your iPhone, if you rebooted your phone, you would be clear in terms of the malware. But generally, when's the last time anybody's rebooted an iPhone? It usually doesn't happen. One of the problems with this chain is that it didn't have any checking that malware was already installed. So it could have the possibility of reinfecting itself and have multiple versions of the payload actually running. And we'll talk about that in the future chains of how they do that. They rely on a kernel task port to get read-write access to anyone with rights for it, which they give themselves rights for it, to corrupt memory, which, like I said, allowed them to write things into kernel space. There is a couple of other ways they bypass policy, and how they do that here is that every device also has a system platform policy that's in there. It's stored on the device in a protected area on the disk, so it can't be modified, but it's only made operational in memory. So if you have access to write into memory, then you could just change the platform policy direct in memory. Again, you don't have persistence, but on the iPhone, it doesn't really matter because few people ever actually reboot their iPhones. So they change the pointer and remove that policy that grants process execution. Then they execute something out of the temp directory using POSIX and start that. They also get around code signing. Earlier jailbreaks of iPhones would simply just modify how the code signing verification works on iPhone devices. But the kernel also has an array of signing blobs of known trusted things that it allows to execute, which it needs to for the kernel and devices on there. They simply just add the signing blob for their code in there to get it to work. So At this point, you've bypassed the sandbox, you bypassed the device policy, and you've bypassed the code signing protection by simply just avoiding the complexity of patching the code signing verification and just adding something to an array that has to exist. These techniques were used across all 5 chains also. So some novelty in terms of how they bypass some of the unique things or unique security features that have an iPhone. So these vulnerabilities, I think, are among the most interesting. The Android ones are relatively straightforward in terms of how they do it, but the iPhone with sandboxing and all that other stuff, there's lots of things that had to be defeated along the way. The second exploit chain started with vulnerable version of 10.3 and was patched in 10.3.4. It abused another kernel bug that had a use after free vulnerability in IO Surface root user client. It is known as the async bug. It was reported publicly and by several people at the same time. But in essence, there wasn't really good code checking where you would, if you called the async method and then checked with another method in Surface root user client, it would drop wake port twice, but make the reference count decremented only by 1. So it wasn't keeping track of its references so that you had dangling pointers. It had, in 10.3, there was a new mitigation for kernel task ports, but it was easily bypassed. So you just made a copy at a different kernel address, and then you could modify what you wanted there. There are some changes also to this exploit chain. In this one, they actually then, when they gave themselves permission to launch processes and bypass the sandbox, after they executed, it would go back in and then make the process tree valid again. I'm not sure why you would do that. You've owned the device. I don't know of any tool that would check for that kind of setting off the top of my head, but they spent the effort to make it cleaner. The second bullet was something that was important on a new development. They put in a boot flag that made no difference to how the device booted, IOPL, but for whatever reason, at least in 10.3, Safari could check boot flags. It was an allowed permission, an allowed function within the Safari browser. So very early on in the process, they would use Safari, check if that boot flag is present, and then just bail out up front without going through the process of re-exploiting the device so that multiple copies of malware wouldn't be running. I can only imagine they got a whole lot of information with exploit chain 1. They decided to make it cleaner and spent real effort and did the first item at the same time for reasons they didn't really need to, but they were thinking of making things cleaner as they went along. Exploit chain 3, they used a different boot argument, IOPL 14. I don't know why they changed it. Just an interesting anecdote that was noticed was they changed a different boot flag. Early on in all of these processes, it would do device enumeration to see how much memory it had because it had relevance to page sizes and the like, what kind of device it was, so it knew what kind of kernel, specific kernel build it was running. So by the very nature of these exploit chains, they only work in defined versions, so I don't know why you would use a different boot flag, but they did, and it's unique where if you knew what to look for, you'd be able to find that a device had been exploited. In this case, it relies on a bound checking error, so an entirely different vulnerability. That came into play when they refactored code, right? This is now iOS version 11 and not 10. So they went back up and refactored code, as people do with major revisions every now and then. And for whatever reason, they changed something from a comparison to a not equal. It made sense to the developer at the time. Theoretically, any kind of code diagnostic tools or fuzzing would have caught this or should have caught it. I have no idea what Apple uses. But ultimately, this helped the attacker escape the sandbox so they can run some of those commands to ultimately execute code on the machine, on the device. So in effect, like I said, they broke their own bounds checking, which should have been caught by standard code diagnostic tools. The attackers then did a heap spray targeting a specific service, Media Server D, because it was accessible to the vulnerable IO kit driver. So they spent real effort going on low level, figuring out how they can get to the next step in there. But a relatively simple error of just changing a comparison allowed them to go further. Fairly simple to fix, but it persisted for a long time between 11.0 and 11.4.1. Exploit chain 4 used a different daemon that wasn't sandboxed in the first place, cfprefs D. It also profounds an unbounded memory move with an argument of a length that the attacker can control, which it should be self-evident why that's an unwise thing. It was only valid for a relatively short period of time between 12.0 and 12.1. That daemon also uses XPC, which allows it to be exploited because it doesn't use that service correctly. And for whatever reason, that wasn't corrected either. Again, a heap and a port spray to exploit the kernel and go through the chain of events to ultimately launch a process. In this case, with 12, they could no longer use boot flags as an indicator that the device was compromised. It was no longer an accessible query in iOS 12. So what they did is change the kernel parameter of the max files per proc setting to 02FF, I believe, off the top of my head. So whatever 256 times 3 is. So if there was a specific string set there or a specific integer set there, they would know the device is compromised, and with a number that high, probably would never impact the device in the real world. In fact, I have no idea why you'd need that many files open per process on an iPhone in the first place. So they changed their boot flag or not the flag they used to detect compromises in that one. Simultaneously with they overlap, not completely, but exploit chain 5 also existed. They only used 4 for a little while because it wasn't as reliable of an exploit. But exploit chain 5 was available from 11.4.1 to 12.1.1. There was only one vulnerability that it had to exploit. It didn't have to go through a couple ones. And this one is the most interesting because it's unclear how this would have happened if you followed any real development methodology. iOS, I think 8, they were starting to introduce the notion of vouchers, but it was never fully implemented and coded. But for some reason, it was still in the code base and shipped. If you actually tried to use it in the conventional way, it would cause a kernel panic and the phone would just lock up and reboot itself. So somehow this partially implemented code got into the code base and shipped out to the world. That's kind of an interesting story. I don't think Apple ever answered the question for that. But they create before, target, and after vouchers and destroy them. But the thread still points to the freed target voucher because it doesn't do the cleanup correctly in the destruction because it wasn't fully implemented. It didn't have all of the hardened checks that you would expect in actual production code to have. They convert the voucher to a port, do another round of that, and ultimately they can create fake kernel tasks in the buffer that have read-write permissions to memory, at which point they can, again, start the process of enumerating process tables, giving themselves permissions to launch outside of a sandbox, changing the system policy, putting things into the array so that they can execute a process out of the temp directory of the same code. So those are the 5 exploit chains that are fairly complicated that I went over relatively quickly. The Android exploits were relatively straightforward. Vulnerabilities in the Chrome browser. Starting from version 39 up to 73, there were gaps of some versions that weren't vulnerable, either because they were patched or because there was some code change that made the exploit not work that was reintroduced into a later version. Chrome 40 wasn't vulnerable, but Chrome 41 was vulnerable to the same exploit in Chrome 39. Ultimately, reduced exploitation to one-click type of operations, right? The user would still have to do something to be victimized, but it was down to one click. Each exploit ran the same shellcode, so in essence, they developed their, their exploit kit as you would in Metasploit, where the vulnerability and the shell code were discrete objects that did different things. And again, operating through hidden iframes in JavaScript. The iPhone malware had access to all the back-end databases on the phone, right? So some of the typical things that you would expect, it had access to the contacts, it had access to photos, it had access to the GPS. The other interesting anecdotes is that often when we think about encrypted messaging apps, we think that they're just encrypted at all places. The reality is that in the SQLite databases on the device, these messages are available in clear text, which theoretically, in a general case, isn't that much of a risk, because if I don't lose my phone and I don't unlock my phone, then somebody can't get access to the underlying SQLite databases. Well, in this case, the attacker gets root, they're on the device, they can see this stuff directly in the clear, and the malware would ship the SQLite database whole and entire to the command and control server. So you got in access to WhatsApp and all the WhatsApp and Telegram were the two encrypted apps. It had access to Facebook Messenger too. It also got access to the keychain, so get things like wireless access point passwords and all the stuff that's in the keychain. It would also take the various long-lived Oauth tokens, at which point, I log into Gmail once, it stores a token on the device, I steal that device, steal it from the device, put it on somewhere else, I've got access to your Gmail account even after you've cleaned up your phone. So even though none of this malware would persist, well actually the Android malware did persist over reboots, we'll talk about that. The iPhone malware didn't, but they stole a lot of Oauth creds to get access to information even after the phone would have been rebooted and cleaned up. That gives them a whole lot of stuff. The various apps it targeted, Viber, Voxer, Telegram, Gmail, QQ Mail, WhatsApp. Those were in the earlier versions that targeted Tibetians. The later versions against the Uighur Muslims included Yahoo Mail, Outlook, NetEase, Mailmaster, which I've never heard about until looking at this malware, Skype, Facebook, and WeChat. So a lot of typical applications that it basically would just ship out the SQLite databases behind that, and then beacon in HTTP in clear to exfiltrate data. There's some commentary about why they would do that in the clear. If you're targeting people inside a regime and you're God on the wires, you don't really have that much of a need of encryption. And encryption gives artifacts that might help correlation. Some versions of the Android stuff did actually use encryption, but they at least the modern versions, I haven't been able to go all the way back, but and enumerate all the SSL certs, they were using Let's Encrypt, which doesn't really give you many artifacts to work with in terms of attribution. The Android malware author apparently likes brown liquor. The whiskey, bourbon, scotch are his monikers. The app was dubbed Moonshine by Citizen Lab. And those are the actual names the malware author gave it for the stages of what their malware did. Whiskey was the initial downloader that tried to unback libbourbon and overwrite a legitimate shared library to give it persistence. So it looked for Facebook, Messenger, WeChat, or QQ, and it would overwrite a specific shared library with libbourbon. Bourbon then would start as part of the app, and it would sideload Scotch as a Java app that did the work of checking in, exfiltrating data, and doing the work of the adversary. It had a hard-coded user agent and uses a unique IP checking utility that's no longer up of getip.name. Haven't seen that, or others haven't seen that lately, but that service is now down. They didn't use the conventional things that most malware authors have done. The last component of this was OAuth targeting. Again, it was malwareless, but it was part of the campaign. It used WhatsApp or Facebook Messenger, wherever it could reach victims. And this was usually more spear phishing than just mass targeting. They were targeting an individual because they were prominent in some way. Would ask them a variety of things. Suppose it's journalists, whatever got them to click a message to then get the OAuth credentials. So in closing, after all of this was publicly reported, almost all of this has been cleaned up and removed from the internet. Things don't resolve anymore. There have been similar campaigns that exploit PCs as opposed to iPhones, but if you were targeting somebody like me for intelligence, you're probably more interested what's on my laptop than what's on my phone. If you're interested in throwing me in a re-education camp, I want to know physically where you are. So that design choice by these attackers highlights the physical risks that these individuals who are compromised make, or the physical risks that they're under. The Android started in 2014. The iPhone started in 2016. But there are a couple of detection techniques you can use. That hard-coded user agent, but I imagine that will be changed in future versions of the malware. But since they use SSL and TLS encrypt for some of the websites anyway, fuzzy searching for key terms that are relevant to Tibet and Uyghur Muslims would give you some proactive detection when people are starting to set up infrastructure that would target those communities. Any questions?